Hello, my name is Kainton Mononye. I'm the computer engineer and also the application developer, and in this video I'm going to be talking about interprocess communication and synchronization mechanisms. These are very important concepts in operating system, and so I decided to make this video for computer science students and anybody that wants to understand these concepts. I'll try to be very clear and to the point, and also I'll explain in simple terms. Interprocess communication, IPC for short. What does it mean? Is a capability supported by operating systems, or for now maybe operating systems generally allow processes to communicate with each other. Okay, so when I discuss the operating system process model, I say the operating system is made up of a number of processes, and now these processes will work with the computer system. The resources are available, and sometimes they have to communicate because they have to share data with each other. So how do you coordinate this communication? How are you sure that this process will share resources in a way that there will be no errors in the operating system? So let's move on to the concept of critical section. Now, what is critical section? Well, just understand, I'm not reading the slides, I'm explaining. So now, if a process is running, okay, a process is loaded in the memory. So at some point in time, the process have to access a shared resources, or a shared resource that is a resource that is being used by more than one process. Okay, so you have a situation whereby a process have to access a shared resource. At this time, we say the process is in its critical section. So what do we say critical section is? I give this definition. A critical section for a process is a point in time when the process have to access shared resources. It may be shared files, it may be shared devices or shared memory location, but at time part of the program when shared memory resources, shared memory is accessed, is called the critical section. So quote my definition here, and that is just fine. Now there is another concept, that is a race condition. Take note of this last sentence. If we could arrange matters such that no two processes were ever in their critical section at the same time, we could avoid race condition. That brings us to the next concept I'm going to discuss in this presentation, and that is race condition. Race condition, race condition is a situation whereby two or more processes are trying to access a shared resource at the same time. So picture it this way: there is a shared file, okay? Process 1 writes data into this shared file and updates it. It means that process 2 writes without knowing that process 1 have written data into it and overwrite whatever process 1 have written there. So that is called race condition. A situation whereby one process uses a shared resource at the same time another process is trying to use a shared resource, and they keep overwriting whatever has been written by the other process. And that's the concept of race conditions. So we have to avoid race condition because it leads to errors in programs. So these are four principles for us to avoid race condition. No two processes will be in their critical section at the same time, okay? And then no process running outside its critical section should block other processes. No process should wait for a very long time before it enters its critical section. Never mind about the explanation of all these. As we discuss along, we are going to get a clear understanding of these 4 points I made here. So how do we avoid race condition? How do we handle interprocess communication? Now there are two ways to do it. Interprocess communication techniques. One, the techniques where we have to require busy waiting. I'll explain this later. We have techniques that require blocking, okay? Now let me explain. Busy waiting means a process is always checking, is a critical section, can it be entered, is another process making use of the shared resource. If another process is making use of the shared memory, then you wait, okay? But you have to be checking from time to time to make sure that the critical section is free. If it's not free, you wait. After some time, you check, you wait, you check. So this leads to busy waiting. So the idle process, or the process that is waiting to enter the critical section, is not just idle. It's not just executing. It's checking. So it's busy checking. Every clock pulse keeps checking. So we have other techniques that requires blocking. We have semaphores, mutexes, monitors, message passing. There are other techniques to avoid to handle interprocess communication, but I think I'll just discuss some of them here. So let's take the first one, disable interrupts. We know that what happens when a process is executing and using the CPU, if it's not interrupted, it's likely it will complete its execution and then release shared resources for another process, okay? Now, if you disable interrupt, okay, it means that if a process is using a shared resource, it prevents itself from being interrupted by another process. Then, when it leaves the critical section, it re-enables the interrupt. So, now let me just read some part of the write-up. The CPU is only switched from process to process as a result of clock or other interrupt. After all, and with interrupt turned out, the CPU will not be switched to another process. So that's it. So if you disable interrupt, you ensure that the process remains there and is not interrupted until it completes. But this is a big problem, because if you disable interrupt, it means a process is telling the CPU, just sit down and relax, I have to do what I want to do. Now if the interrupt is not re-enabled and this process continues to execute forever, it means that the CPU, the system, is going to crash. So disabling interrupt is not the optimal solution to handle interprocess communication. So let's look at another one, a log variable. Log variables is a variable that takes two values. It can be 0, it can be 1. So it means that if a process wants to access a shared resource, it sets this log variable to lock. Let's say 0 being 1 being locked. So it means if another process wants to access a shared resource, it checks the log variable. If it's locked, no way, you just wait. Okay? So once the process using the shared resource finishes, it comes out and it resets the log variable to 0. So another process checks. If it's 0, it means the critical section is free. So this is about log variable, a variable that can be set to 0 or 1, on or off, to lock or unlocked, to show the critical section is in use or is free. So strict alternation is another process. It means processes execute in a round-robin manner. So after one process executes, it switches to the next process. So it means that we can just have a variable called turn. Okay, so turn have a value that it keeps track of whose turn it takes to enter the critical section. So if it's process 0, 1, 2, 3, so it checks, each process checks the turn. If it's your turn, or the turn variable is set to your process ID, you enter the critical section. Patterson solution have this data structure. I did not specify here, but we have enter region and also leave region. Enter region is a data structure or a procedure. You call it with your process ID, and then you enter the critical section. Once you are done, you call another process, data procedure leave region, and you're able you leave. So once you call enter region, another process tries to call it. It finds out that the critical section can't enter its critical section, so you have to wait until the current process completes the task it's performing and leaves the region. So it's implemented using two data structures or two procedures, enter region and leave region. For simplicity, I'm not going to present the code here. So we have another technique called sleep and wake up. So now we want to eliminate busy waiting. So if a process wants to access the shared resource or wants to enter the critical section, okay, what does it do? It enters the critical section and calls sleep for other processes. Okay, so instead of for other processes to be busy checking when the critical section is free, they are sleeping, so the CPU time is not wasted. They are not busy checking nothing. So when the process finishes and assessing the shared resource, it simply calls other process wake up, and then they assess the shared resource. So they sleep and wake up. Now we have another technique we call semaphores. Semaphores is a very important topic in operating system. Semaphore is simply either a variable or an abstract data type, that is a data structure. Okay, it's used for controlling resources that is shared by multiple users or multiple processes. Semaphore is a data structure provided by the operating system. So it's not a data structure that is written by the programmer. It's implemented by the operating system. And what does it do? A semaphore operation ensures that the operation that is being executed is atomic. So check, okay, the critical section, enter, leave, everything is atomic. So there is no interruption until the process completes the task and then comes out. So if operation is in a semaphore, okay, it has to be completed. It can't be interrupted or overwritten, and that is the functionality provided by the operating system. Now mutex is a kind of semaphore. Monitors, I'm not going to explain much, but just take note, monitors are like semaphore. The only difference between monitors and semaphore, a monitor is a construct provided by the programmer. A semaphore is implemented by the operating system, but in the way they operate in a similar way. Message passing, I think this should be the simplest way. So the process communicates by passing message between themselves. So we have these two sends. You send to another process a message, are you free? Can I enter? It replies, no, you can't enter. It sends another message, are you free now? Can I make use of the resource? The receiver receives, say, I received your message, yes, you can enter now. So message passing is another way to implement interprocess communication, where the processes in the operating system share the message between themselves using the send and receive procedures. Well, I hope this has been informative for you. I'd like to thank you for viewing. My name remains Kainton Munonye, and I'd like to remind you to subscribe to my channel, leave comments, ask me any question in operating system. Once again, I'd like to thank you for viewing.